Okay, the Physics 1 FRQ problems have been released for 2021, and I want to go through some possible solutions to each of the problems. So here's problem number 1. It says that there is a stunt cyclist, and they build a ramp that will allow the cyclist to coast down the ramp and up over several parked cars as shown. To test the ramp, the cyclist starts from the top of the ramp, leaves the ramp, jumps over 6 cars, and lands on a second ramp. So this is like a projectile problem where the cyclist will leave the end of the ramp at some position with some initial velocity. Call that v naught. That velocity at an angle has two components. So you know that anytime there's a vector at an angle, you can break it down into the components that make it up. There's a horizontal velocity and a vertical velocity component. The horizontal distance that the cyclist will travel from here to here is dependent upon the horizontal velocity component. We'll call that v sub x, and that's a constant velocity for the whole trajectory. The time that it takes for the cyclist to get from one ramp to the other ramp depends upon the initial vertical velocity. We'll call that v naught y. So this is actually a fairly complicated derivation. I'm a little surprised that this is a problem that appears on the AP exam. It's toward the most complicated of the derivations that has appeared in recent years. What you need to do is figure out how fast the cyclist leaves the end of the ramp, and that is going to be dependent upon the height from which the cyclist starts. So we have this gravitational potential energy up here, and that gravitational potential energy changes into kinetic energy. However much gravitational potential energy the cyclist has at the top is going to be exactly the same as the kinetic energy at the end of the ramp here. How far down the cyclist goes in this dip is completely irrelevant. The velocity at the end of the ramp depends only upon this difference in height. So the first thing you can do is deal with the law of conservation of energy problem and say that the gravitational potential energy at the top of the beginning of the ramp is equal to the kinetic energy at the bottom. The gravitational potential energy of the cyclist is equal to mg. I'll write this in terms of the variables that are described in the problem. M naught is described as the mass of the cyclist and the bicycle, although you'll see that doesn't matter, times g times the height from which the cyclist drops relative to the end of the ramp, and that's equal to 1/2 m naught, and then that's, I'll write v naught squared, where v naught is the initial velocity at which the cyclist leaves at the ramp here. The masses of the cyclist and the bike is completely irrelevant. The masses cancel out, and you'll find that the speed that the cyclist leaves the end of the ramp is equal to the square root of 2g h naught, just like that. So that's the speed at which the cyclist leaves the end of the ramp. The two components of the velocity, v sub x, as I've defined it in the problem, is going to be equal to v naught cos theta. This angle here, theta, is the angle of the ramp from the horizontal. So it's both this angle here and this angle here. Those are exactly the same angle because they're, well, like alternate interior angles. So v naught cos theta is equal to v sub x. And then that's the same as square root of 2g h naught cos theta, and v sub y is equal to v naught sine theta. So that's square root of 2g h naught sine theta. Okay, the distance that the cyclist ends up traveling is just based upon the definition of velocity. Average velocity is equal to the displacement over the time, and the horizontal velocity is constant. So this v sub x is delta x over delta t, is a constant value. And we're trying to figure out what the horizontal distance is. In this problem, it's defined as x naught. So x naught is equal to v sub x t. I already have an expression for v sub x. It's the square root of 2gh naught cos theta. So that's square root of 2g h naught cos theta That's the horizontal velocity. And then the time is the time that it takes for this person to get from the top of the ramp to the top of the next ramp. It's the time it takes to go up and then back down. So you have a kinematics problem. And in this kinematics problem, you leave the surface of the ramp with some initial velocity, v sub naught y, which is equal to 2g h naught sine theta. You have an acceleration rate equal to g. The velocity at the top is 0. So you're trying to find the time that it takes to get to the top. And you can use the equation v squared is equal to v naught squared plus 2a delta y. Oop, no, actually we don't want that. We'll just do v equals v naught plus at. So the speed at the top is 0. The time it takes to get to the top is equal to v naught over a. The v naught is the initial vertical velocity, and the initial vertical velocity is 2g h naught sine theta over g. Acceleration is g. Now the thing you need to keep in mind is this is the time that it would take to get up to the top. The time it takes to get from the apex back down to the ramp is exactly double the amount of time. So this time here is not the time it takes to get from the top of the ramp to the apex of the arc. This is the apex, but it's the time that it takes to make the entire flight, which is exactly twice as long as this time. So it's twice as much as square root of 2g h naught sine theta over g. Put this all in a big parenthesis. So this is a pretty complicated expression. We have a 2, and then because there's the square root of 2g h naught that twice, it's really the square root of 2g h naught squared, which is just 2g h naught. And then we have a sine theta and a cos theta. So we have sine theta, cos theta, and that's all over g. So one more step of simplification is I got 2 times 2 is a 4. These g's cancel out. 4 h naught sine theta cos theta. And I think that that would be an acceptable derivation. But there's one more little step that you could do, and this is not on the equation sheet, and you wouldn't necessarily be expected to know this trig identity, but it is true that 2 sine theta cos theta is equal to sine 2 theta. And you can try this out on your calculator, just test some kind of angle, and you have to be in degree mode. I mean, you can also be in radian mode, but if you want to do it as degrees, if you do like 2 sine 20 cos 20, you get 0.642, or if you do the sine of 40, it's the same thing, 0.642, 0.643. So instead of 2 sine theta cos theta, you could substitute sine 2 theta. Well, this 2 is half of the 4, so you could go one step further and write 2 h naught sine 2 theta. I would venture to guess that you would get all the credit for this expression here. You would still get the same credit, I believe, for this expression. I really cannot imagine that you would lose a point for not knowing that 2 sine 2 theta is the same as, sine 2 theta is the same as 2 sine theta cos theta. All right, anyway, so that's a pretty good expression for 1A, and to be honest, 1A is probably the most difficult thing in the whole test because you need to know the law of conservation of energy and not get tripped up that this vertical distance doesn't matter at all. Know to take the initial vertical velocity on the ramp and break it into the two components to make it up, and know how to calculate the time to the top. There's an equation called the range equation that you could use, but the range equation is not on the equation sheet. It's not a thing that you normally memorize, and a lot of students have a difficult time with projectiles anyway. So I would say that this expression is probably the most difficult part of the AP test, and that's 1A, so it might be a little bit discouraging, like straight off the bat. All right, I'm going to take this equation and copy it because we're going to use that maybe in the next problem. Okay, so here's the expression that we derived. It looks like that the horizontal distance that traveled is equal to 4h0 sine theta cos theta. So this problem says that the vertical distance between the top of the first ramp and launch point is 2h instead of h0. With no other changes to the first ramp, what's the maximum number of cars that the stunt cyclist could jump over? Justify your answer using the expression you derived in part A. So it looks like x0, the horizontal distance that you travel, is directly proportional to h0. So if x0 is proportional to h0, then 2x0, or I guess you could say 2h0 is gives you 2x0. If you double the value for h0, you double the value for the horizontal distance that you travel. So what is the maximum number of cars the stunt cyclist could jump over? Here it looks like there are 6 cars. The problem also says that there are 6 cars. So as long as they're equally spaced, you could jump 12 cars. The important thing to say is justify your answer using the expression you derived in part A. You answer, you could jump over 12 cars. And the reason is that the horizontal distance is directly proportional to the vertical difference in height from the beginning of the cyclist path to the end of the ramp where the cyclist becomes a projectile. And if you double h0, then x0 doubles. That's what you would say. On the axes below, sketch a graph of the vertical component of the stunt cyclist velocity as a function of the time from immediately after the cyclist leaves the ramp to immediately before the cyclist lands on the second ramp. So if the cyclist is a projectile, and you have this motion which is like that, the initial velocity is like v0, and you have a initial horizontal velocity which is constant v sub x, and there's this vertical velocity which you leave v sub 0y. At the very top of the trajectory, all of the velocity is only horizontal, v sub x. And when the cyclist lands, they land at exactly the same angle, theta, and with exactly the same speed, which is, well, I guess you could say it's negative. Well, I'll just write this. It's the same as v0 if it's the speed. There's a horizontal velocity, v sub x, but now the vertical velocity, v sub y, is equal to negative of whatever v0 y was. So if the initial vertical velocity is positive, the final vertical velocity is negative. You don't know how much time it takes, so you could use any distance on this graph, but it's always best to fill the graph up. So what I'd recommend is, define the initial vertical velocity, which is v sub naught y, and I would put that right up here. So this is v sub naught y, and then at the apex, which is going to be halfway through in time, the vertical component of the velocity is 0. In other words, the cyclist is neither going up nor down. For all of this part here, you have a v sub y component that's negative, or that's positive. That's for all of this distance and time. And for all of this distance and time, v sub y is negative. So the final velocity in the vertical direction is equal in magnitude to the initial vertical velocity. And like always on the AP exam, you always use a straight edge, a ruler, or a straight piece of paper to draw a perfectly straight line. So there's a perfectly straight line. That way the reader can hold a ruler up to it. Now it says on the vertical axis, clearly indicate the initial and final vertical velocity components in terms of h0, theta naught, m naught, and physical constants as appropriate. So what would not be acceptable is to write like v sub naught y and v sub y, because here I've labeled the y-axes as the value for the initial vertical velocity and the value for the final vertical velocity. That's not what the prompt says. The prompt says to clearly indicate the initial final vertical velocity components in terms of h naught, theta naught, and m naught. So we don't want those values. What we want are values that represent the initial and final vertical velocities. I'll go back to this part here, and it looks like what we want is the vertical velocity is derived just like that. And we'll go ahead and stick that in here. So the vertical velocity is equal to the initial vertical velocity times the sine of the angle, or the square root of 2g h naught sine theta. So the prompt says that we want the vertical velocity components in terms of h naught, theta naught, and m naught. So we only need the variables h naught, theta naught, and m naught. Now it turns out that the vertical velocity is independent of the mass. So just because it says that you can use m naught, you don't necessarily have the value m naught in the value. So v sub y initially is positive, and it's redundant to put the positive sign, but it's not bad to write it. So I'd write positive square root 2g h naught, and then you want to clearly show that that radical ends times the sine of theta. So that little vertical thing tells that it's done. See, if you write this, it's not exactly clear if the sine theta is inside the parenthesis, and if you start drawing this over a little bit like that, especially if it's partly over the sine theta, it's not clear if it's in the sine theta or not. So it's always smart to have like that little tiny thing there, which indicates that that's the end of the radical. The velocity at the end is negative square root of 2g h naught, h naught sine theta. So now I've satisfied what the vertical axis values must be. They must be in terms of h naught. So I have an h naught, theta naught. There's theta naught. I guess I put little knots in there. Theta naught. M naught, there is no mass, and physical constants as appropriate. A physical constant includes g, and it's always okay to include, square roots and the number 2 and whatnot. Okay, so that's that. I don't think we have to include the... Yeah, we don't have to say in terms of time here, but I wouldn't imagine it would be bad to say that, this time is the takeoff. This time is at the apex, and this is the time at the landing. Because you're prompted to include those bits of information in the problem, or include the line showing from takeoff to landing. It's self-explanatory, but it's smart to, maybe say takeoff, apex, landing. You would not get points taken off for that, I don't suppose. I really can't imagine how that would happen. All right, so that's problem number 1. It's a doozy, especially the derivation, but even if you can't get the derivation for the whole thing, you should be able to correctly plot this line. And even if you can plot the line but not have the values correct over here, you'd still get some points for the line, just as long as it would have to be a straight line. And the slope of a velocity time graph gets you the rate of acceleration, and this rate of acceleration in the vertical direction is provided by gravity. And you would not include this on the graph, but just as an aside, the slope of that line is equal to, in this case, delta v over delta t. It's equal to the acceleration rate, and the slope of that would have a value of negative 9.8 meters per second squared. That's just as an aside. If you were to write that, you wouldn't want to put that in the graph. If you were to write that, you wouldn't get points for that necessarily, because you're not prompted to do it, but that's what the slope of the line would happen to be. Okay, that's problem number one.